Okay, so in chapter 13, we're going to piggyback off of what we discussed in chapter 12, the analysis of variance. And this time we're going to talk about two factor analysis of variance. So the analysis of variance evaluates the differences among two or more sample means. And in chapter 12, we talked about the ANOVA being a single factor that's limited to one independent variable or one quasi independent variable. And those independent measures look at the study uses a separate sample for each of the different treatment conditions being compared. While the two-factor independent measures ANOVA is a complex analysis of variance that has two independent variables which are manipulated. Both of those independent variables and quasi-independent variables may be employed as factors in the two-factor ANOVA, and an independent variable or factor is manipulated in that experiment. A quasi-independent variable or factor is not manipulated, but defines the groups of scores in a non-experimental study. And those two factors ANOVA allows us to examine three types of mean differences with one analysis. We can have a factorial design which considers more than one factor. We will study those two-factor designs only, and we're also limited to situations with equal numbers in each group. You can also have a joint impact of factors, which must be considered with the two-factor independent ANOVA. There are three hypotheses that are tested by three F ratios. The larger F ratio is greater treatment differences than would be expected with no treatment effects taking place. So the three F ratios have the same basic structure. You have the numerator, which measures the treatment mean differences, and the denominator, which measures the treatment mean differences when there is no treatment effect, as indicated at the bottom of the screen. The main effects are the mean differences among levels of one factor. Those differences are tested for statistical significance, and each factor, factor A and B, is evaluated independently of the other factors in the study, as indicated by those formulas at the bottom. We can also have interactions where the mean differences between individual treatment conditions or cells are different from what would be predicted from the overall main effects of the factors. If the null hypothesis is rejected, there is no interaction between factors A and B. And if the null hypothesis is accepted, that means there is an interaction between those factors A and B. The interaction can be defined as a unique effect of two factors that are working together, and the alternative definitions are slightly different perspectives. If the two factors of independence are independent, one factor doesn't influence the effect of the other, then there is no interaction. When the two factors are not independent, so the effect of one factor depends on the other, then there is interaction, and this can be seen in a graph. When it comes to the dependence of factors, the effect of one factor depends on the level of value of the other factor, and those unique combinations of the factors produce unique effects. The interaction can be observed in a graph, and those non-parallel lines that cross, converge, or diverge, indicate the interaction is occurring. And that's also called the A times B interaction or the A by B interaction. So we have figure 13.2, which is a graph that shows us the treatment means for table 13.3 in the textbook, for which there is no interaction, so there's no crossing of lines. And then here's figure 13.2, which is a graph for table 13.4, which shows there is interaction, and we can see those two lines crossing. The independence of main effects and interactions indicate that there are three distinct tests that are being used: the main effect of A, the main effect of B, and the interaction of A and B. And a separate F test is conducted for each, the results of one are independent of the others, as indicated by the formula listed at the bottom. So let's go ahead and do a learning check. Which of the following accurately describes an interaction between two variables? Is it A, B, C, or D? And hopefully you thought D. The effect of one variable, it depends on the level of the second variable. And In figure 13-1, an example of those two factors, ANOVA and the effect size. The A effect is the main effect of factor A. That's typically what evaluates the mean differences between the rows. The B effect is the main effect of factor B, which typically evaluates the mean differences between those columns. And the A by B interaction evaluates the mean differences between treatment conditions that are not predicted from the overall main effects. And for an example of the two-factor ANOVA and effect size, we've got the first stage, which is identical to the independent samples ANOVA. And then we've got the second stage, which is the partition of the sum of squares between the treatments into three separate components. And in figure 13.3, we can see the structure of the analysis for a two-factor ANOVA. And we can also see the stage one of those two factors with those formulas that are indicated. And then for stage two, we can also see what determines the numerators for those three F ratios with looking at the sum of squares between those treatments. And there's continuation of those sum of squares, but with the degrees of freedom. And here are the mean squares and F ratios for those two-factor ANOVAs. If we look at table 13.7, it's a summary table for the two-factor ANOVA for the data that's used in example 13.2. A hypothesis test for the two-factor ANOVA follows the same four-step procedure that we've seen before in all of the other different tests. We've got you first state the hypothesis and select an alpha level. Then you locate the critical region, compute the F ratios, and make a decision. So for the effect size for the two-factor ANOVA, we first compute a value for eta squared and the percentage of variance that's explained by the treatment effects. And the report means and standard deviations are usually in a table or graph or due to the complexity of the graph. You report the results of all three hypothesis tests. And for each test, you include the capital F, the D, the degrees of freedom, the p-value, and n squared. When we interpret the results from a two-factor ANOVA, we have to focus on the overall pattern of the results. Significant interactions require particular attention because even if you understand those main effects, those interactions often go beyond what main effects alone can explain. The extensive practice is typically required to be able to clearly articulate those results that include a significant interaction. And we can see from figure 13.4 those sample means for the data in sample 13.2. Let's go ahead and do another learning check. Which of the following accurately describes the two stages of a two-factor ANOVA? Is it A, B, C, or D? And hopefully you thought D. The first stage partitions the total variability, and the second stage partitions the between treatment variability. Testing simple main effects are some of the other ways we can look at the two-factor ANOVA. And those simple main effects are a separate analysis for each of the individual columns and rows that test the significance of the mean differences within one column or row of a two-factor design. The two-factor experiment is separated into a series of separate single-factor experiments. It's done when there's a significant interaction, when the mean differences between one column show different patterns than the mean differences between another column. Participant characteristics such as age and gender may vary considerably from one person to another. Participant characteristics can influence the scores obtained in the study, and there's a large variance that tends to reduce the size of the T statistic or F ratio and therefore reduces the likelihood of finding significant mean differences. A solution to the problem of high variance uses the specific variable associated with consistent individual differences as a second factor. Instead of one group in each treatment, the researcher divides the participants into two separate groups within each treatment. One factor consists of the two treatments, and the second factor is, for example, based on gender or on age. The validity of the ANOVA depends on three assumptions that are common to other hypothesis tests, the t-test, and the single factor ANOVA. The observations within each sample must be independent of each other. The populations from which the samples are selected must be normally distributed, and those populations from which the samples are selected must have equal variances, known as homogeneity of variance. So let's go ahead and do another learning check. If a two-factor analysis of variance produces a statistically significant interaction, then you can conclude what? Go ahead and take a few moments to think about the correct answer. And that correct answer is going to be D. The significance of the main effects is not related to the significance of the interaction. And let's try a true false. Two separate single factor ANOVAs provide exactly the same information as obtained from a two-factor analysis of variance. And a disadvantage of combining two factors in an experiment is that you cannot determine how either factor would affect participant scores if they were examined in an experiment by itself. So take a few moments and think about both of those choices. And the correct answer is going to be false and false. The main effects in a two-factor ANOVA are identical to the results of the two one-way ANOVAs, but a two-factor ANOVA produces the interaction results too, and the two-factor ANOVA allows you to determine the effect of one variable controlling for the effect of the other. And in figure 13.5, you can see the ANOVA for an independent measurer's two-factor design and how that formula will look once you calculate all of those things. And that is everything I need you to know about those two-factor ANOVAs. Hopefully this information helps.